Hi there and back again. This is chapter 11 of the DB2 course. We have seen in the first video of this chapter that grouping and sorting are quite related operations. So given that we have a workable sorting implementation, for example, external merge sort, we could use that to implement grouping. And that's why we are talking about grouping in this particular part of the course. There is also other methods to implement grouping, for example hashing, and we will briefly touch on this in the coming few minutes. And we will in particular discuss how PostgreSQL decides whether to use sorting or whether to use in-memory based hashing to perform the grouping. Okay, so just to remind you of what grouping is all about, well, grouping in a sense coarsens the granularity of data processing that we perform with SQL. So, well, say that you've got an input table. This is our new playground input table for the playground query 10, which is exactly this particular query. So say you've got an input table of 1 million rows. Then grouping this particular table by a grouping criterion like column G here will coarsen the granularity. Many of these rows will fall into the same group because they share the grouping criterion. And well, after grouping, only individual groups are being output by SQL. Okay, so not every row will be seen in the output, but only every group will be seen. So normally what we will see is a substantial reduction in cardinality, in output cardinality. So for example, a 1 million row table might only lead to 10,000 groups. So about 100 rows form one group in this particular example. All of this could happen. Right. So what we are tasked with is partitioning the input rows in our group table. The partitioning criterion, of course, is the grouping criterion column G here. All rows agreeing on G form one group. Okay. And once we have formed the partitions, what we will then do is to aggregate all the rows inside one group. As you may recall, we will never see the individual members of a group after a SQL group by query has been processed. All that we will see is the grouping criterion itself, which is digit column G here, and an aggregate like the sum aggregate or the max aggregate or the min or the average aggregate of all the rows inside the groups. This is what leads to the output cardinality reduction that we observe. Okay, so it's all about the efficient implementation of this particular operation, grouping. And well, as I already mentioned, there's at least two ways in which we can implement grouping inside a relational database system. You will find both ways implemented in virtually all systems out there. Also, PostgreSQL implements both methods. So let's have a quick look at both alternatives here. Okay, so we are left with this input table, our input grouped table with, say, two columns. One of the columns, the G column, makes for the grouping criterion. So all rows agreeing on the grouping criterion will form one group. So how to process it? Well, in at least two ways, either in the sorting way or in the hashing way. Okay, so above the line sorting. What we'll do is we will sort the input regarding its grouping criterion, and how we could do that is obvious now. We would probably use external merge sort or maybe in-memory merge sort if the input file is small enough. What we would end up with is a table, a temporary result table that is of course ordered in ascending G fashion here, in ascending G order. Now it's very easy to identify the group boundaries for us. All right. Obviously, this would be one such group boundary, and this would be one such group boundary. Inside each group, all rows would agree on their G value. Once we have performed this intermediate sort step, we would just scan the sorted table from top to bottom in the order of ascending G values. While we do that, we would perform all the aggregation computation. So if you recall our Q10 Pro query, there was the task of summing all the A values. And that's what we will do while we scan the file, this intermediate sorted file, the intermediate sorted table here. Of course, we will reset the aggregate every time we cross one such group border. Okay, so inside the group that agrees on G equal 11, we will add up all the A values, and we will finally end up with an A value, a sum of A values of 8. This would be the sum that is associated with the grouping criterion G11. We would then reset the sum to enter the next group, which will only consist of a single row here. So the sum of A values for our grouping criterion 38 would be A equals 5. This is exactly this 5 over here. All right, and then the 3-element group with G equals 42, we would add up all the values and again end up with an overall sum of 8 for all the A values. Right, so it's very easy to scan the sorted result, to detect the boundaries of the groups, to reset all the aggregates. We could compute more aggregates than just the sum here while we go in one particular scan. All of this should be rather obvious. The other method of evaluation would be hashing. Okay, so to bring all those values close together that share the grouping criterion, we would apply a hash function to the G column here. Okay, all values that agree on the G column will of course lead to the same hashing value. Okay, so let's assume that the hash function will map a G value of 42 to key K1. So the hash of 42 will be the key K1. All right, so all of the rows with the G value of 42 will end up in this key 1 hash bucket, and the A values will contribute to the sum that we maintain in this bucket for the G value 45. Of course, there could be hash collisions, and other G values, for example the 38 here, might also be mapped to the key 1. This is what's called a key hash collision. All right, so in the same bucket, in the bucket for the key K1, we will also find an entry for our value G equals 38, and we will maintain the sum there. There's not much to maintain, it's only a single entry, and we would end up with a 5 here. Other values, other G values would map to different key values and thus to different buckets. And well, our hope is that the number of collisions is small and that the space that we allocate inside this hash table is evenly used. You see, this is not the case in this particular crafted example, but I think it should convey the general idea. So sorting and hashing, as so often in algorithmics, are dual concepts that we can replace with each other. It's no different in the case of the evaluation of group bys. Okay, so how does PostgreSQL decide whether to use sorting or whether to use hashing? Well, this will depend on the current state of the system and the configuration of the system. For example, the decision will be based on the size of the available working memory. Okay, if the working memory is really scarce, if there's very little working memory available, then there won't be space to allocate large hash tables to maintain all the different keys, their buckets, and the entries. So in the case of very, very scarce working memory, this would be this particular case, we would end up using probably sort-based grouping, probably based on external merge sort, which can cope with very little working memory. The same is true if we expect the number of groups, the estimated number of groups to be large. This again will lead to large hash tables with lots of entries. And well, maybe that many entries that indeed we would rather, well, exceed the available working memory, and in this case we would rather refrain from using hash-based sorting and a hash-based grouping, and would rather build on external sorting instead. All right. Well, if the number of groups is expected to be modest, or if we have plenty of working memory, then the construction of a hash table is a very attractive option. And well, you will see that PostgreSQL then decides to indeed use in-memory hashing and try to avoid any external I/O that might be incurred by external sorting. Right. Often this number G, capital G, the number of groups that will be constructed, the number of rows in the output cardinality of the grouping, how much coarsening is actually going to occur. Often this number G is unknown, or it cannot be derived properly. All right. So let's assume we are looking at a group by criterion that looks like this. Well, looking at this and knowing about the properties of the modular function, we would be able to tell that the number of groups that is being constructed here is indeed less than 3. It's a maximum of 3. So a G value of 0, a G value of 1, and a G value of -1. All of these are, or a grouping criterion value of 0, -1, or 1 are the only grouping criteria that can be the result of this computation. So a maximum of 3 groups will be constructed, but unfortunately this is not understood by PostgreSQL. So PostgreSQL would have to have knowledge about the expected output cardinality of arbitrary applications of its arithmetic operators or expressions in general, and this is not built into PostgreSQL. So you will see that the system quite often overestimates G, the number of groups that will be produced, quite conservatively, and you will see PostgreSQL to resort to sorting quite often, even in cases where hashing should indeed be an option, because the number of groups will be low. Okay, to see this in action and to get some insight there, and to see how PostgreSQL can in some cases indeed forecast the correct number of expected groups, let's switch over to the terminal. Okay, so here we go. In this session I have already prepared this new playground table group, and indeed it's a 2-column table with columns A and G. Column G will be our grouping criterion, while column A will be the column over which we compute aggregates here. I have already inserted 1 million rows as indicated on the slide, and indeed I have produced a grouping criterion G here that will lead to 10,000 rows. Okay, so this modular operation by 10,000 will of course lead to exactly 10,000 groups if we group by column G here. Okay, I've already analyzed the situation. Let's look at the table here. Indexes are not of concern currently. Of course, an index on the G column could be used to perform a grouping by G here, but let's not look at this particular case here. It's all about hashing and sorting here. Okay, right, so let's look at the currently available working memory. I think it should be in the default state, like 4 megabytes. There you go. Okay, so if we perform grouping now with plenty of working memory, and the 4 megabytes in this case would be considered plenty of working memory, then let's see what we observe. According to the mini decision tree that we have seen on the slides, we should probably see an in-memory hash operation being applied here. Okay, let's see. Okay, so we scanned all the groups of the table grouped. Okay, and indeed all the rows flow into a hash aggregate implementation. So this is indeed a hash-based implementation of grouping. The grouping key is G, as we expected, while we construct and while we insert the rows into the hash buckets. What we maintain there is the grouping criterion G itself, and the sum of A values that we have found inside each group. Both are needed to then finally emit the final result of our SQL query. And that is also the root of our query plan. There's not anything else to do here. Okay, what you can see is that indeed the system estimated that the overall result will have about 10,000 rows. So this is quite a good estimate already. The system estimated that the coarsening of granularity here would lead us to about 10,000 rows. Once the system evaluated the query and then indeed constructed the result, it indeed saw that 10,000 rows after grouping would be the result. But this estimate is not too bad. And given 4 megabytes of memory, the system estimated that an in-memory hash would be the way to go here. Alright, so now let's be mean to the system again, like so many times already, and reduce working memory to, well, 1/8 of that, only half a megabyte, 512 kilobytes. Okay, and now it's time to just repeat this same query. I think this is working memory that is so scarce that the decision of the system will now be different, and it will favor the sorting based grouping. All right, takes a bit longer already. I think double the time, about double the time here. All right, so let's see. Indeed, this is again a scan of the grouped table, and we can already see, yes, the rows flow into a sorting operation here. Of course, the sort key is the grouping criterion G. We will need an external merge sort because working memory is so scarce. We of course sorted all the 1 million rows. All of this can be seen here. After the grouping is indeed now based on a group aggregate, which maybe would better called a sort aggregate. This is an implementation of the grouping that is based on the sorted input that can be scanned from top to bottom, and while we scan, we detect the group boundaries. This is behind this group aggregate implementation. The system estimated that it will generate 10,000 groups here, which is the same estimate as before, and of course the system found itself to generate 10,000 groups. All right. So this is too large a number of groups to maintain this inside a hash table given this little working memory. So now let's clue in the system, or try to give the system some clue that the expected number of groups is way smaller than 10,000. Let's use this as the grouping criterion. This is actually the grouping criterion that was mentioned on the slide. And if you have some insight into the semantics of the modulus operation and the type, the input type of this particular G column, then you will see that the maximum number of groups that can be constructed here is indeed 3. Okay, -1, 0, and 1 are the only values that the grouping criterion can take on. So a maximum of 3 groups should be constructed. This should indeed fit. This should indeed fit into a hash table that can even fit into 512 kilobytes of working memory. So let's see what happens. Well, the Frony doesn't bode well here. And indeed, what we find is a sequential scan that feeds its row into an external sort operation, just like we've seen before. This time, the sorting criterion is, of course, the group criterion again. It's a G divided, or a modulo of 2 of G. Right. There's actually a very nice optimization to be seen here. You see that the sequential scan does not output G, it will output the modulo of 2 of G, which is a clever thing to do because the modulus of 2 of G is all that is needed later on in the plan. G is irrelevant, the modulus of 2 G regarding 2 is relevant, and this is already computed down here in sequential scan so that the rest of the upper level nodes in the plan don't have to recompute this value again. So that's a nice optimization, but still we are using external sort, and the reason is that the estimate of the number of groups that PostgreSQL estimates still is at 10,000, which of course does not fit the semantics of the modulus operation, but the query optimizer is not aware of the semantics of the modulus, and so its estimate is conservative, which leads to the use of the external sorting. Okay, so if we are now a bit more explicit about the number of groups that is to be expected here. So let's use a different sorting criterion. You see that the sorting criterion in this last query is of type Boolean. Okay, so this is exactly a sorting criterion that asks whether the G value is indeed even or odd. And there's only two outcomes there. This is the Boolean, only two outcomes are possible. The system knows about the active domain of the Boolean type, which is just, well, it's 3. It's true, false, or null. But the system knows about the possible outcome of this expression. It knows about the domain size, and it knows that the number of groups that is to be expected is really small here. Okay, so let's see what happens now. Recall that the working memory is still scarce. Okay, this went quicker than the queries before. Indeed, the sequential scan is super clever and already emits the Boolean, not the value of column G or the value of the modulus. It indeed emits the Boolean here, which is the best thing that the sequential scan was able to do. And indeed, it feeds the output of the sequential scan into a hash aggregate. So although we are scarce on working memory, the system did the correct forecast that there will be a maximum number of groups of 2. Well, there is no null group here because G is indeed not null. The analysis of the column G has shown that. So this is the expected number of groups. This will even fit into the tiniest working memory, and hash aggregation is indeed the method of choice in this particular case. And we are of course rewarded by improved execution times. 2 seconds were this 6 seconds. All right. Okay, so much for our initial impression of grouping. There is more to be said about grouping, because grouping is an operation that lends itself to very clever parallelization strategies, and that's something that we want to explore in the next video. So much for sorting and grouping here in these videos. Hope you will be around when we deepen our discussion on grouping and then also switch over to MonetDB again. See you then.